Take a ruler and picture the smallest thing it could measure. Now imagine a smaller ruler and a smaller one after that, halving the distance each time. You feel like you could do this forever. You cannot. There is a length so small that below it the words longer and shorter stop meaning anything the universe will let you check. It is called the Planck length, and it sits about 20 powers of 10 below the width of a single proton. Over the next couple of hours we'll build up to why it exists, slowly, one plain step at a time, starting from 3 numbers that were hiding in plain sight. If you like the idea of taking one thing and understanding it all the way down, consider subscribing and stay with me. Our question is simple, and the whole climb answers it. Why can't you measure anything smaller than this? Hold a ruler in your hand and find the smallest mark on it. On most rulers, that mark is a millimeter, about the thickness of 2 sheets of paper pressed together. You can already picture something finer than that. Take the gap between 2 marks and split it in half in your mind. Now you have half a millimeter. Split that half again, and then again. Nothing in the act of halving seems to push back. Your hand could keep dividing forever, and for most of human history people assumed that space itself would let you. This assumption is older than physics. The ancient Greeks argued about it. Some, following the philosopher Zeno of Elea, worried that if a distance could be divided without end, motion itself became a puzzle. Others, like Democritus, guessed that matter must come in smallest pieces, and gave those pieces a name, the atom, meaning the thing that cannot be cut. But even Democritus imagined his atom sitting in a smooth, endlessly divisible space. The stuff might be grainy. The distance between grains, he thought, was not. For 2,000 years that picture held. When you learn geometry in school, you inherit it. A line is made of points, and between any 2 points there is always another, packed in without limit. Mathematics is happy to divide a length as many times as you like. You can write down a number as small as you wish, put more zeros after the decimal, and the number still means something on paper. The page never complains. So here is the honest question this whole story turns on. Is the world like the page? When you halve a real distance in the real universe, and then halve it again, does the cutting go on without end, or does something eventually stop your hand? For a long time, no one had a reason to think it would stop. Space looked smooth. It looked like the geometry in the textbook, only larger. The surprise, the one we will spend the next couple of hours earning, is that the cutting does stop. There is a length so small that below it the very idea of a shorter distance stops meaning anything you could ever check. Not because our rulers are clumsy, and not because our eyes are weak, but because of the way 3 of the deepest facts about nature fit together. Reach that length, try to look closer, and the universe answers by hiding the answer from you. That length has a name. It is called the Planck length, after the German physicist Max Planck, who stumbled onto the idea more than a century ago while thinking about something else entirely. We will meet him properly soon. For now, hold on to one number and let it sit with you even though it means nothing yet. The Planck length is about 1 6/10 times 10 to the minus 35 meters. That string of words hides a smallness so extreme that no comparison from ordinary life quite reaches it, and we will spend a whole chapter later just trying to feel how small it is. What matters first is the shape of the claim. This is not a limit of our tools. A better microscope will not save you. A sharper ruler will not save you. The flaw is written into the rules of the game, the same rules that set the speed of light and the strength of gravity. To measure below the Planck length, you would have to break the universe's own agreement with itself. We will get there one step at a time, and every step will rest on the one before it. Start here, with your hand splitting a distance in half, feeling like it could go on forever. Keep that feeling close. By the end you will understand exactly where it fails, and why the failure is not a flaw in you, but a feature of the world. That number, 1 6/10 times 10 to the minus 35 meters, did not come from measuring anything. No one laid a tiny ruler against the world and read it off. It was built, on paper, out of 3 other numbers, and those three numbers are among the most important in all of physics. Think of them as three fixed facts about how the universe is put together. The first is the speed of light, the fastest anything can travel, written in physics as the letter c. The second is Newton's gravitational constant, which sets how strongly mass pulls on mass, written as the letter g. The third is Planck's constant, which sets the size of the smallest steps energy comes in, written as the letter h, or in the form we will mostly use, h bar. Each of these is a number nature seems to have chosen and then held fixed everywhere, for all time, in every experiment anyone has ever done. Now here is the quiet piece of magic. Each of those three constants carries its own units, its own flavour of measurement. The speed of light is a length divided by a time. Newton's constant mixes length, mass, and time in its own particular way. Planck's constant mixes them differently again, and it turns out that there is exactly one way to multiply and divide these three together, so that the mass cancels and the time cancels, and what you're left with cleanly is a length. Do that, and out drops the Planck length. You take h bar, multiply it by g, divide by the speed of light 3 times over, and take the square root of the whole thing. The units line up perfectly, and the number that falls out is that impossibly small distance. You can do the same trick and land on a time instead, or a mass, or a temperature, or an energy. Each is called a Planck unit, and each is built from the same 3 keys. Sit with how strange that is. We did not go looking in the small world and find a smallest length. We wrote down 3 constants that were discovered for completely separate reasons, in completely separate corners of physics, and we asked a simple question. Is there a length hidden in their combination? There was. It fell out on its own, without anyone deciding it should be special. That is the part worth holding on to. The 3 constants were not invented to make this length. The speed of light came from studying light and motion. Newton's constant came from studying falling apples and orbiting moons. Planck's constant came from studying the glow of hot objects. They belong to 3 different stories, yet when you press them together, they agree on a scale, a single distance where all 3 of their worlds seem to meet. Physicists have a name for the suspicion this raises. When a length falls naturally out of your deepest constants, you start to wonder whether nature itself pays attention to that length. Maybe it is just an accident of arithmetic, or maybe it marks a real edge, a place where the ordinary rules stop working and something new has to take over. For reasons we will build up carefully, most physicists lean toward the second reading. This length seems to matter, but before we can trust the answer, we have to understand the question, and that means understanding the 3 constants themselves, one at a time. Where did each come from? What does each really say about the world? Why does the speed of a light have a ceiling at all? And why is gravity so absurdly weak? And what does it mean for energy to come in steps? Each of these is a story with a person behind it, and each story is worth telling slowly, so we will take them in turn. But first, we should meet the man whose name this length carries, and hear how he came to the idea in the first place. In the last year of the 1800s, a careful German physicist named Max Planck was turning over a problem that had nothing to do with tiny lengths. He was 41 years old, a professor in Berlin, known for being precise, conservative, and deeply serious about the foundations of his subject. He loved music, played the piano well enough that a career had once seemed possible, and approached physics the way he approached a score, looking for the deep order underneath. Planck had been thinking about units, the human business of measurement itself. And something about the ordinary units bothered him. A meter was once tied to the size of the Earth, then to a metal bar kept in France. A second came from the turning of our particular planet. A kilogram was a lump of metal in a vault. Every one of these was an accident of human history and human bodies. If we ever spoke to a distant civilization that had never seen our planet or our metal bars, none of our units would mean anything to them. Planck wanted units that would. He wanted a system of measurement that any intelligent being anywhere in the universe could reconstruct from scratch, using only the deep constants of nature. Not the length of a king's foot, not the swing of an earthly day, something built from the speed of light, from the constant of gravity, and from a new constant he himself had just uncovered while studying the glow of hot bodies. So around 1899, Planck wrote them down. He combined those constants and produced a natural length, a natural time, a natural mass, and a natural temperature. He called them natural units precisely because they owed nothing to us. He wrote that these quantities would keep their meaning for all times and all cultures, even non-human ones, and could rightly be called natural units of measurement. It was a beautiful and almost philosophical idea, and at the time, that is mostly what it was: philosophy. Because here is the honest part. Planck did not know what his natural length meant physically. He did not claim it was the smallest possible distance. He did not connect it to any limit on measurement. He simply noticed that the constants gave you a length, an astonishingly tiny one, and he found that worth writing down for its elegance. The deep significance we now attach to it, the idea that the universe forbids measuring below it, came decades later from other people, using physics Planck could not yet have known. That gap matters, and it's a good example of how physics really moves. A person sets down an idea for one reason, often an aesthetic one, a sense that something is clean and right. Then the idea waits, years pass, new physics arrives, quantum mechanics and general relativity, and someone looks back at the old idea and sees that it was pointing at something far deeper than its author realized. Planck gave us the length. The universe supplied the meaning slowly over the following century. Planck himself would go on to a hard and honored life. His work on hot bodies opened the door to quantum theory, the very revolution that would eventually give his little length its teeth. He won the Nobel Prize. He also lost a great deal, including a son to execution in the last days of the Second World War, and he carried his losses with the same quiet steadiness he brought to his physics. The unit that bears his name sits at the far frontier of what we can understand, which feels fitting for a man who spent his life reaching toward the foundations. But if we are being fair, and this story tries hard to be fair, Planck was not actually the first to think this way. Someone had built natural units from the constants of nature years before him, and that person is usually left out of the telling. He deserves a chapter of his own. Almost 20 years before Planck, an Irish physicist named George Johnstone Stoney had the same instinct and followed it just as far. Stoney worked in Dublin, and today he is remembered, if he is remembered at all, for a single word. He gave us the word electron. He proposed it as the name for the basic unit of electric charge, years before anyone had actually found the particle it would come to describe. When the particle turned up, the name was waiting for it. But Stoney did something else that history has been slower to credit. In the early 1880s, he too grew dissatisfied with human units, and he too went looking for a set built from nature's own constants. His starting point was slightly different from Planck's. Where Planck would later reach for the constant of gravity, the speed of light, and his radiation constant, Stoney reached for the charge of the electron, the speed of light, and Newton's constant of gravity. From those he built a natural length, a natural time, and a natural mass. His natural units came out close in spirit to Planck's, and remarkably close in size for the mass. Stoney's length was somewhat larger than the one Planck would find, because he built it from charge rather than from the quantum constant Planck had not yet discovered. But the ambition was identical. Stoney wanted, as he put it, units of nature, quantities that an intelligence anywhere in the cosmos could arrive at independently, because they rested on facts the whole universe shares. It is the same dream Planck would later be celebrated for. Why then do we call it the Planck length, and not the Stoney length? Part of the answer is timing and luck. Stoney worked before the quantum revolution, so his units, built on charge, could not connect to the new physics that was about to arrive. Planck's units, built on his radiation constant, turned out to sit exactly where quantum theory and gravity would later collide. Planck had, without knowing it, reached for the right ingredient. And part of the answer is simply that Planck was more central to the physics that followed, more visible, more cited. History keeps the name that is easiest to keep. There is a lesson in this that goes beyond fairness to one Irishman. The clean stories we tell about discovery, one genius, one moment, one name, are almost always simplifications. The real path is crowded. Ideas arrive early, in forms that do not quite fit, and wait for the rest of physics to catch up. Stoney reached the doorway first. Planck walked through it into a house that had not been built yet, and the house, when it rose, took his name. Stoney's own life was that of a serious, productive scientist of his era. He estimated the charge on a single unit of electricity decades before it was measured directly, and his number was in the right neighbourhood. He worked on the physics of gases, on optics, on the motion of molecules. He raised a scientific family, and he carried quietly the distinction of having imagined natural units of measurement before the man whose name they now carry. We tell this part not to take anything from Planck, who earned his place many times over, but because a story about the deepest limit of measurement should itself be measured honestly. The Planck length has a prehistory. It did not spring from one mind. It grew from a shared instinct, held by more than one careful person, that the universe should be describable in terms that belong to the universe and not to us. With that debt paid, we can turn to the three constants themselves. Because whatever we call the length, it is only as meaningful as the ingredients that build it. And the first of those ingredients is the one that sets the ceiling on all motion. The number that Einstein would show is woven into the shape of space and time. We begin with the speed of light. Light is fast in a way that outruns our intuition. Flick a switch and the room fills instantly, or so it seems. In truth, the light took time to cross the room, about 100 millionth of a second, far too brief for you to notice. Light travels a little under 300,000 kilometers every second. In 1 second, it could circle the Earth roughly 7.5 times. It crosses from the sun to your eyes in about 8 minutes, which means you always see the sun a little in the past. For most of history, no one knew light had a speed at all. It seemed to arrive everywhere at once. The first real measurement came in the 1670s, when a Danish astronomer named Ole Romer noticed that the moons of Jupiter seemed to run early or late depending on how far Jupiter was from Earth. He reasoned that the light carrying their image took longer to reach us when Jupiter was farther away. From the timing, he got a speed. It was rough, but it was real, and it settled a long argument. Light was fast, but it was not infinite. That number, the speed of light, sits at the heart of our story, and it took Albert Einstein to reveal how strange it truly is. In 1905, Einstein built his theory of special relativity on a single stubborn fact. The speed of light is the same for everyone, no matter how they are moving. Chase a beam of light as fast as you like, and it still races away from you at the full speed of light, not one bit slower. That sounds impossible, and following it honestly forces you to give up ideas you thought were solid. What has to give is the notion that time and distance are fixed. To keep the speed of light the same for every observer, moving clocks must run slow, and moving lengths must shrink. And two people moving differently can disagree about which events happened at the same moment. Space and time bend and trade off against each other to protect that one number. The speed of light is not really about light. It is the conversion rate between space and time, the fixed exchange that ties them into a single fabric. And from this comes the ceiling. Nothing that carries mass can be pushed all the way up to the speed of light, because the closer you get, the more energy each extra bit of speed demands, rising without limit as you approach. Push forever, and you get closer, but you never arrive. The speed of a light is the universe's hard upper bound on how fast cause can chase effect. No signal, no object, no influence of any kind outruns it. This ceiling is the first of the three facts we need. Hold it plainly. There is a fastest speed, it is woven into the structure of space and time, and it is written into physics as the letter C. Every clock, every ruler, every signal in the universe answers to it. Now notice why a speed limit matters for a story about a smallest length. To measure where something is, you have to send a signal to it and get one back, and that signal can travel no faster than light. To pin down something very small, in a very short time, you press against this limit. Space and time are not the free, endlessly stretchable backdrop we imagined when we halved that ruler. They are governed by a fixed speed, and that fixed speed will turn out to be one of the three walls that box in the smallest measurable length. But the speed of light alone is not enough to build the Planck length. It sets a ceiling on motion, but it says nothing about the graininess of energy or the pull of gravity. For the length to appear, we need a second constant, one that came from a completely different puzzle, the puzzle of why hot things glow the colours they do. That puzzle is where Max Planck earned his constant. Heat a piece of iron, and it begins to glow. First a dull red, then orange, then a bright yellow-white as it gets hotter. Every hot object does this, from a stove coil to a star, and by the end of the 1800s, physicists desperately wanted to explain the exact colours. They had good theories, and the theories failed in a spectacular way. When they used the accepted physics to predict how much light a hot object should give off at each colour, the math said it should pour out an infinite amount of energy at the blue and violet end. Obviously it does not. A warm oven does not blast you with lethal ultraviolet. The prediction was not slightly wrong. It was impossibly wrong. Max Planck found the fix in 1900, and he found it almost by accident, calling it an act of desperation. He assumed, as a mathematical trick to make the numbers behave, that the hot object could not give off energy in any amount it liked. Instead, energy came out only in discrete little packets, whole steps, never a fraction of a step. The size of each step depended on the colour of the light, and the whole thing was governed by a new constant, a very small number that he was forced to introduce to make the sizes come out right. That number is now called Planck's constant. It is fantastically small, about 6 6/10 times 10 to the minus 34 in the standard units, a decimal point followed by 33 zeros before the digits begin. Its smallness is why we never notice the steps in ordinary life. Energy seems perfectly smooth to us for the same reason a sandy beach looks smooth from a distance. The grains are there, they are just far too fine to see. Planck thought his packets were a bookkeeping trick, a way to get the right answer that would surely be explained away by smoother physics later. But the trick was true. 5 years on, Albert Einstein took it seriously and showed that light itself comes in packets, later named photons, and that this explained another stubborn puzzle, the way light knocks electrons out of metal. The steps were real. Energy, at the smallest scale, is grainy. This was the birth of quantum mechanics, the physics of the very small, and it changed everything. The constant carries a name and a meaning worth stating plainly. Planck's constant sets the size of the smallest unit of action in the universe, action being a particular blend of energy and time. It tells you the scale at which the grainy, packet-like nature of the world becomes impossible to ignore. Above that scale, things look smooth and continuous. Below it, the world comes in steps and behaves in ways that would look like madness in the ordinary world of tables and chairs. For our purposes, there is a slightly refined version of the constant that shows up again and again, called the reduced Planck constant, written as h bar, which is just Planck's constant divided by a certain fixed factor. It is the form that appears in the deepest equations, including the recipe for the Planck length. When we combine the constants at the end, it is h bar that carries the quantum piece into the mix. So now we hold two of the three keys, the speed of light, which fixes the ceiling on motion and ties space to time, and Planck's constant, which reveals that energy and action are grainy, coming in smallest steps. One is the constant of relativity, the other is the constant of the quantum world. These two theories, relativity and quantum mechanics, are the two great pillars of modern physics, and they do not sit together comfortably. Where they are forced to meet, trouble begins, and the Planck length lives exactly at that meeting point. But we still need the third key, and it comes from the oldest and most familiar force of all, the one that holds you in your chair and swings the moon around the Earth. Yet as we will see, it is also, by an enormous margin, the weakest. Gravity does not feel weak. It pins you to your chair. It makes a fall dangerous and a climb tiring. It holds the oceans down and swings the entire moon around the Earth month after month. It feels, in daily life, like the strongest thing there is. And yet, of the four fundamental forces in nature, gravity is by an enormous margin the weakest. It is not a little weaker than the others. It is weaker in a way that is genuinely hard to believe. Here is a demonstration you have already done without noticing. Take a small magnet, a cheap one from a refrigerator door, and hold it above a paperclip. The magnet lifts the clip clean off the table. In that moment, one tiny magnet has won a tug of war against the gravity of the entire planet. The whole Earth, pulling down with all its mass, loses to a scrap of magnetized metal you could lose in your pocket. That is how badly gravity is outmatched by electromagnetism, one of the other forces. The number that measures gravity's strength is Newton's gravitational constant, written as the letter G, and it is our third key. Isaac Newton, in the 1680s, wrote down the law that every mass pulls on every other mass, and that the pull grows with the masses and fades with the square of the distance between them. But he could not say how strong the pull was in absolute terms. The constant G is the missing number that sets the actual strength, and Newton never knew its value. It took about a century more to measure it. In the 1790s, an intensely shy English scientist named Henry Cavendish built a delicate apparatus, two small lead balls on a beam, hung by a thin fibre, with two large lead balls brought near them. The faint gravitational tug between the balls twisted the fibre by a tiny angle, and from that twist Cavendish worked out the strength of gravity, and with it the mass of the whole Earth. He did this alone, in near silence, being a man so withdrawn he could barely speak to his own housekeepers. His measurement was so good that it stood, barely improved, for a century. The value he was closing in on, Newton's constant, is a very small number, about 6 7/10 times 10 to the minus 11 in standard units. That smallness is the mathematical face of gravity's weakness. Gravity only becomes a giant when you pile up an unimaginable amount of mass, a planet's worth, a star's worth. Between two everyday objects it is there, always, but so faint that it took one of the most careful experiments of the age to feel it at all. Now hold the strange picture we have built. Gravity is the weakest force, so weak that a fridge magnet beats a planet. Yet gravity is also the force that will slam the door on measuring below the Planck length. How can the weakest force in nature enforce the deepest limit on physics? The answer is that gravity has one property the other forces lack. It responds to energy itself, and it never turns off, and it never repels, only attracts. Pile up enough energy in a small enough space, and even the weakest force wins, catastrophically, by folding that region into a black hole. We will build up to that carefully. For now, we simply add the third key to the ring, the speed of light, the ceiling on motion, Planck's constant, the graininess of action, and Newton's constant, the strength, or rather the astonishing weakness of gravity. 3 numbers from 3 separate stories, discovered by different people in different centuries for different reasons. The remarkable thing is what happens when you finally put all 3 together. They lock. There is one, and only one, way to combine them into a length, and that length is the smallest the universe will let you speak of. It is time to put the 3 keys into the single lock. We now have 3 constants in hand, and each one carries its own kind of measurement baked into it, like an accent that reveals where a person is from. To see how they combine into a length, we do not need heavy mathematics. We only need to track those accents and watch them cancel. Start with what each constant is made of. The speed of light is a distance divided by a time. If you know how far light goes and how long it takes, you have its speed. So the speed of light carries 1 unit of length, and hidden underneath, 1 unit of time in the denominator. Planck's constant, in its reduced form h bar, carries a blend of mass, length squared, and time, the particular mix that makes up what physicists call action. And Newton's constant carries its own blend of length, mass, and time, arranged so that when you multiply 2 masses and divide by a distance, you get a force. Now think of it as a puzzle in cancellation. We want to end up holding a pure length, with no leftover mass and no leftover time clinging to it. So we have to combine the 3 constants in just the right proportions so that every unit of mass on top is matched by a unit of mass on the bottom, and every unit of time is likewise wiped out, leaving only length standing. It turns out there is exactly one combination that does this. You take h bar and multiply it by Newton's constant. That mixes the quantum grain of action with the strength of gravity. Then you divide by the speed of light multiplied by itself 3 times over, which is to say the speed of light cubed. When the dust settles, the masses cancel, the times cancel, and you're left with a length squared. Take the square root, and out comes a plain, honest distance. That distance is the Planck length. There is no freedom in this. You cannot choose a different mixture and get another length just as natural. The units only balance one way. This is why physicists find the result compelling rather than arbitrary. We did not tune the recipe to reach a target. We demanded a length, insisted that mass and time cancel completely, and the 3 deepest constants in physics answered with a single, unavoidable value, and you can play the same game to reach other quantities. Combine the 3 constants a little differently, so that only time survives, and you get the Planck time, the shortest meaningful interval. Arrange them so only mass survives, and you get the Planck mass. So only energy survives, and you get the Planck energy. Each is a natural unit, each built from the same 3 keys, each marking a scale where the ordinary picture is expected to break down. The Planck length is simply the one that speaks most directly to our question about measuring distance. Step back and notice what this really says. The presence of the speed of light means relativity is involved, the physics of space, time, and motion. The presence of Planck's constant means quantum mechanics is involved, the physics of the grainy small, and the presence of Newton's constant means gravity is involved. All 3, together, in one number. The Planck length is the scale at which relativity, quantum mechanics, and gravity are all shouting at once, none of them quiet enough to ignore. That is the deep reason the length matters. In ordinary physics, we get away with using one theory at a time. When we study a falling ball, we use gravity and ignore quantum steps. When we study an atom, we use quantum mechanics and ignore gravity, because gravity between such tiny masses is beyond negligible. The Planck length is where that convenient separation collapses, where you would need gravity and the quantum world described in the same breath, and we do not yet have a theory that can do it. Before we face that collision, though, we should feel the sheer size of the number we have built, or rather, the sheer smallness. We keep saying the Planck length is small. Now let us try to actually feel it, because the number 1 6/10 times 10 to the minus 35 meters is just a string of words until you build a ladder down to it. The trouble is that the ladder is longer than any we normally climb, and each rung drops you 1,000 times smaller, or 10,000, and still you are nowhere near the bottom. Begin with something you can hold. A human hair is about 1/10 of a millimeter across, thin enough that a single strand is easy to lose. To reach the scale of a single atom, you have to divide the width of that hair by about 1,000,000. An atom is that much smaller than a hair, and already we have left everything the eye can ever see. No microscope that uses ordinary light can show you a single atom, because atoms are smaller than the light waves themselves. Now go smaller. Inside the atom, almost all of it empty space, sits a tiny dense core, the nucleus. To get from the size of the whole atom down to the nucleus, you divide by about another 100,000. The nucleus is a speck at the centre of a vast, mostly empty atom. If the atom were the size of a sports stadium, the nucleus would be a marble at the very centre. And inside that nucleus sit the protons and neutrons, each about 1 7/10 times 10 to the minus 15 metres across. We have now shrunk from a hair to an atom to a proton, dividing by 1,000,000 and then by 100,000, and by any human standard we have reached the absolute basement of smallness. The proton is about as small as anything we have ever directly probed, and here is the part that should stop you. From the proton, you still have to go down about another 20 powers of 10 to reach the Planck length. 20 more factors of 10. The Planck length is smaller than a proton by roughly the same ratio that a proton is smaller than a small city. Let that comparison sit. Imagine a whole city, kilometers across. Now imagine a single proton somewhere inside it. The proton is unthinkably tiny against the city. The Planck length is that much tinier again, against the proton. We have stacked one dizzying smallness on top of another, and only then do we arrive at the floor. There is another way to feel it, by looking up instead of down. The observable universe is about 90 billion light-years across, a distance so vast that light itself, our fastest messenger, needs billions of years to cross even a fraction of it. Ask how many Planck lengths would fit across the entire visible universe, and the answer is a number with about 60 digits. Ask how many Planck lengths fit across a single proton, and the answer has about 20 digits. The Planck length is as far below the proton as it is, in a sense, below almost everything. It is the true floor of the scale. This is why no ordinary comparison quite works. When we say a virus is small, we mean small next to a cell. When we say an atom is small, we mean small next to a virus. Each step is a factor of thousands. The Planck length is not one more step down that familiar staircase. It is dozens of steps past the last rung anyone has ever stood on, into a region no experiment has ever touched, and, as we will see, perhaps no experiment ever can. So when we ask why the universe forbids measuring below this length, we're not asking about a difficulty of a few extra decimal places. We're asking about a floor set impossibly far beneath the smallest thing we know. And to understand why the floor is there at all, we have to change the question. We have to ask what it even means to measure something, to see it, to pin down where it is. Because seeing, it turns out, is a kind of hitting. Think about what it means to see anything at all. Right now, light is streaming from some source, bouncing off the objects around you and landing in your eyes. You never touch the chair across the room. You catch the light that bounced off it. Every act of seeing is really an act of catching something that has ricocheted off the thing you want to look at. To observe is to bounce a probe off your target and read what comes back. This is fine for a chair because the light that bounces off it is far too gentle to move it. The chair does not flinch when you look at it, but shrink the target down and this comfortable arrangement falls apart. To see something very small, you have to hit it with your probe, and the probe carries energy, and that energy shoves the very thing you're trying to locate. Looking is no longer gentle. Looking becomes a collision. Picture trying to find a marble in a completely dark room, using only a stream of other marbles that you roll across the floor. You roll them out, and when one clatters off in an odd direction, you know it struck the hidden marble. From the bounce, you can figure out roughly where the marble is, but notice what you have done. In the very act of finding it, you have knocked it to a new spot. The harder and faster you roll your probing marbles, the sharper your sense of the collision, but the harder you kick the target away. Precision in place comes at the cost of disturbing the thing. This is the deep trouble at the heart of measuring the small, and it is not a matter of clumsy equipment. It is built into what observation is. You cannot look without touching, and you cannot touch without disturbing. For large objects, the disturbance is nothing. For the smallest objects, the disturbance is the whole story. Now bring in the nature of light. Light behaves as a wave, with a certain wavelength, the distance from one crest to the next. and a wave is a clumsy tool for finding anything much smaller than its own wavelength. Think of ocean swells rolling past a thin post sticking out of the water. The long swells barely notice the post. They roll straight past as if it were not there, carrying no clear imprint of it, but send in short, choppy ripples, and they break and scatter against the post, and now the water carries a clear sign that something is there. To probe fine detail, you need short waves, so to see something small, you need light with a short wavelength. And here the two ideas we've been building start to close in on each other. From Planck and Einstein, we know that light comes in packets, and that shorter wavelength light carries more energy per packet. Red light, with its long waves, is gentle. Blue light is stronger, ultraviolet stronger still. X-rays and gamma rays, with wavelengths short enough to probe inside atoms, carry ferocious energy in every packet. Put the two facts side by side. To locate something small, you need short waves. But short waves mean high energy, and high energy means a hard shove to whatever you're trying to pin down. The finer the detail you want, the more violently your probe strikes the target. There is no gentle way to look closely. The universe has tied precision of place to violence of disturbance and knotted them together at the deepest level. This knot has a name and a precise mathematical form, given to us by a young German physicist working through a hay fever-stricken retreat on a barren island in the 1920s. Before we reach him, though, we should look at the simplest place this limit shows up, a place scientists met it long before quantum mechanics. It shows up in the ordinary microscope, and in a hard rule about what a microscope can and cannot ever reveal. The microscope is one of the great instruments of science. It opened the world of the cell, the microbe, the crystal. But every microscope, no matter how finely made, runs into a wall, and the wall is set by the light it uses. A microscope cannot show you anything much smaller than the wavelength of the light passing through it. Build the lenses as perfectly as you like, polish the glass to flawlessness, and this limit still stands because it comes not from the glass but from the light. The reason goes back to the ocean swells and the post. Visible light has a wavelength of around 500 nanometers, which is to say about 500 billionths of a meter. That sounds small, and it is far smaller than anything your unaided eye can resolve, but it is enormous compared to an atom. A single atom is a few thousand times smaller than the wavelength of visible light. So visible light rolls past an atom the way a long swell rolls past a thin post, barely disturbed, carrying home no clear picture of it. You simply cannot photograph an atom with visible light. The light is too coarse a brush. This was understood in the 1800s, well before anyone spoke of quantum limits. A German physicist named Ernst Abbe, working with the lens maker Carl Zeiss, worked out the rule precisely. The smallest detail a microscope can resolve is set by the wavelength of the light and the geometry of the lens, and no cleverness with the glass can beat it. If you want to see finer detail, the rule says, you must use light with a shorter wavelength. There is no other way through, so scientists did exactly that. They reached for shorter and shorter waves. Ultraviolet light, with a shorter wavelength than visible, could resolve a little finer. Then came the X-ray, with a wavelength short enough to reveal the arrangement of atoms in a crystal, not by making a picture directly, but by reading how the crystal scattered the rays. It was with X-rays that the double helix shape of the DNA molecule was finally teased out, because their wavelength was fine enough to feel the spacing of the atoms. But every step to a shorter wavelength was a step to higher energy, exactly as we saw. Visible light is gentle. Ultraviolet carries more punch. X-rays carry enough to knock electrons loose and damage the very sample you're studying. The instrument that sees most finely is also the one that hits hardest. The microscope, in reaching for smaller detail, is forced to strike its subject with ever more energetic probes. The gentleness of ordinary looking is gone. There is a device that pushes this idea further, the electron microscope, and it is worth pausing on, because it quietly uses the next idea we need. Instead of light, it uses a beam of electrons, and it can resolve detail far finer than any light microscope. That seems strange at first. Electrons are particles, little bits of matter, not waves. How can a stream of particles do the job of short wavelength light and do it better? The answer is that particles are not simply particles. A moving electron has a wavelength of its own, and that wavelength gets shorter the faster the electron moves. Speed the electrons up, and their waves grow finer, fine enough to resolve individual atoms. The electron microscope works because matter, like light, has a wave hidden inside it. That single idea that every particle carries a wavelength came from a French physicist thinking about symmetry, and it is one of the strangest and most beautiful ideas in all of physics. But before matter waves, we should meet the principle that made the disturbance we keep circling into an ironclad law. Ernst Abbe's limit was about lenses and light. The deeper limit, the one that will not bend for any instrument, came from Werner Heisenberg, and it turned the knot between position and disturbance into one of the firmest rules the universe has. In the summer of 1925, a young German physicist named Werner Heisenberg was miserable with hay fever. To escape the pollen, he retreated to Helgoland, a small, rocky, nearly treeless island in the North Sea, where the air was clear. There, alone, working through the nights, he built the mathematics of a new mechanics for the atom. He was 23 years old. Out of that work and the work that followed with others came one of the most famous and most misunderstood ideas in science, the uncertainty principle. The principle makes a sharp claim. There are pairs of things about a particle that you cannot both know perfectly at the same time. The clearest pair is position and momentum, where momentum means, roughly, how much motion a thing carries, its mass times its velocity. The more precisely you fix a particle's position, the less precisely its momentum can be defined, and the other way around. Pin down exactly where it is, and its motion becomes wildly, genuinely uncertain. Pin down exactly how it is moving, and its location smears out across space. This is not a statement about clumsy measurement, though it is often told that way. It is not merely that our probes disturb the particle, true as that is. Heisenberg's principle says that the particle simply does not possess a perfectly sharp position and a perfectly sharp momentum at the same time. The sharper one becomes, the fuzzier the other must be, as a fact about what the particle is, not about how well we happen to see it. The trade is built into nature, and there is a number that sets the terms of the trade. The product of the uncertainty in position and the uncertainty in momentum can never fall below a certain amount, and that amount is set by Planck's constant, the same grainy constant from the glowing iron. Our old friend h-bar sets the floor on the bargain. Because Planck's constant is so tiny, the trade is unnoticeable for anything large. A thrown baseball has a perfectly definite position and motion for all practical purposes. But for an electron, the trade dominates everything. Now connect this to seeing the small. To locate a particle within a tiny region, to say it is here and nowhere else, you must fix its position very precisely. But the uncertainty principle says that the more tightly you box in its position, the larger and more uncertain its momentum becomes. Squeeze a particle into a smaller and smaller space, and it thrashes harder and harder, its motion growing wilder as its position sharpens. Confinement for a quantum particle means agitation. Here is the same idea from the side of the probe. To pin a particle's location to within some small distance, you have to hit it with a probe whose wavelength is at least that short. And a short wavelength, as we saw, means high momentum and high energy. So the very act of locating the particle precisely floods it with energy. The uncertainty principle is the ironclad version of the knot we found earlier. Precision of place and violence of disturbance are not just practically linked. They are linked by law, with Planck's constant setting the exchange rate. Follow this to its end, and you can feel where it is heading. To measure a length as small as the Planck length, you would have to confine a probe to that fantastically tiny region, which by Heisenberg's rule would require a fantastically large momentum, and therefore a fantastically large energy. crammed into a fantastically small space. The smaller the distance you want to resolve, the more energy you must concentrate into a smaller and smaller point. That road leads somewhere the earlier physicists could not have foreseen. Cram enough energy into a small enough space, and gravity, the weakest force, finally has its say. But before gravity enters, we need to understand the wave hidden inside every particle, the idea that lets a probe reach small distances in the first place. That idea belongs to a French aristocrat named Louis de Broglie. In 1924, a French physicist named Louis de Broglie put forward an idea so bold that his own examiners were not sure what to make of it. De Broglie came from an aristocratic family, a genuine noble line, and had come to physics somewhat late, after first studying history. His idea was a stroke of pure symmetry. Physicists had recently learned that light, long thought to be a wave, also behaves like a stream of particles, the photons. De Broglie asked the mirror question: if waves can act like particles, can particles act like waves? He proposed that every particle of matter, an electron, a proton, anything, has a wavelength, and he gave a simple rule for it. The wavelength of a particle is set by its momentum. The more momentum a particle carries, meaning the more massive it is or the faster it moves, the shorter its wavelength. A slow, light particle has a long wave, a fast, heavy particle has a short one, and the constant that connects momentum to wavelength is, once again, Planck's constant. The same small number keeps appearing at every doorway in this story. It sounded like fantasy, and it might have been dismissed, except that it was quickly proven true. Within a few years, experimenters fired electrons at a crystal and watched them scatter into a pattern of bright and dark rings, the exact kind of pattern that only waves produce when they overlap and interfere. Electrons, undeniably particles, were behaving as waves, with precisely the wavelength de Broglie had predicted. For that thesis, once nearly rejected, de Broglie received the Nobel Prize. This is the idea that quietly powers the electron microscope, and it is the idea that lets us reach ever smaller distances. Remember the rule that you cannot resolve detail finer than the wavelength of your probe. With de Broglie's insight, we're no longer limited to the wavelengths of light. We can use particles, and we can shorten their wavelengths simply by speeding them up. Give an electron more momentum, and its wave grows finer, sharp enough to probe smaller and smaller structures. So the recipe for looking deeper becomes clear. To see smaller things, use particles with shorter wavelengths. To get shorter wavelengths, give the particles more momentum. To give them more momentum, accelerate them to higher energies. Each of these steps is the same step said a different way. Smaller distances demand higher energies. The number that ties them together is Planck's constant, and the relationship is not a loose trend but a strict rule. Halve the distance you want to resolve and you must roughly double the energy of your probe. You can see now why physics built ever larger machines to look ever smaller. It seems backward that seeing the tiniest things requires the biggest instruments on Earth, machines kilometers around, but it follows straight from de Broglie. To reach a smaller wavelength, you need a faster particle, and to make a faster particle, you need a longer runway to accelerate it and stronger magnets to steer it. The size of the machine grows as the size of the target shrinks. The two run in opposite directions, tied together by energy. And this sets up the great question that drives the rest of the climb. If smaller distances always demand higher energies, then measuring down to the Planck length would demand an energy so vast it is hard to write down. How vast, and what happens when you actually try to concentrate that much energy into that smaller space? That is where the story turns from the familiar physics of microscopes and accelerators towards something far stranger. But first, let us follow the practical path as far as it actually goes. Humanity has built machines to chase de Broglie's waves down to smaller and smaller sizes. The largest of them sits in a tunnel beneath the border of two countries, and it is worth seeing just how deep it reaches, and how impossibly far it still remains from the floor we are chasing. Beneath the countryside on the border between France and Switzerland runs a circular tunnel, about 27 kilometers around, buried deep underground. Inside it sits the Large Hadron Collider, the largest and most powerful machine humanity has ever built for looking at the small. It is the direct descendant of de Broglie's idea. It takes particles, in its case protons, and drives them to enormous energies, giving them fantastically short wavelengths, so they can probe the tiniest structures we have ever resolved. The way it works is the way we have been describing, scaled up to the limit of engineering. Protons are injected into the ring and accelerated lap after lap by electric fields that give them a push each time around. Powerful magnets, cooled to colder than deep space, bend the speeding protons to keep them on the circular path. Around and around they go, gaining energy, until they are moving at very nearly the speed of light. A hair's breadth below that ceiling relativity sets. Then two such beams, running in opposite directions, are steered into each other, and the collisions are watched by detectors the size of buildings. Why collisions? Because at these energies, looking and smashing become the same act. The protons carry so much energy, packed into such short wavelengths, that when they strike, they probe the structure of matter at scales far smaller than the proton itself. The debris that sprays out of each collision carries the record of what happened at that tiny distance. It was in machines like this that the quark structure inside protons was mapped, and it was in the Large Hadron Collider that the Higgs boson was finally found in 2012, the particle tied to how other particles get their mass. Each discovery came from reaching a smaller distance by reaching a higher energy, so how small can it see? The Large Hadron Collider probes distances down to roughly 10 to the minus 20 meters, or thereabouts. That is a genuine marvel. It is about 10,000 times smaller than a single proton. We have taken de Broglie's waves and driven them a full 4 powers of 10 below the proton into a realm no natural process on Earth reveals. By any ordinary reckoning, this is the frontier of the small, and now place that frontier against the floor we are chasing. The Planck length is about 10 to the minus 35 meters. The Large Hadron Collider reaches about 10 to the minus 20 meters. Between the deepest our greatest machine can see and the Planck length lie about 15 more powers of 10. 15 more factors of 10. The gap between the collider's reach and the Planck length is far larger than the gap between the collider's reach and the width of your hand. Let that settle, because it is the crux of the practical problem. We built a machine 27 kilometers around, cooled colder than space, running at nearly the speed of light, to reach 10 to the minus 20 meters. To reach the Planck length by the same method, we would need to keep multiplying the energy, and each factor of 10 smaller in distance costs another factor of 10 in energy. To close 15 more powers of 10, the energy required climbs to a level no conceivable machine could reach. We will put real numbers to that climb later, and they are staggering. This is the first hint that the Planck length is not merely hard to reach, but perhaps impossible to reach by the only method we know. The method itself, higher energy for smaller distance, works beautifully all the way down from a hair to the inside of a proton, but it is a road that gets steeper without end, and the Planck length sits at a place on that road we may never climb to. Yet the truly deep barrier is not the cost of the machine, it is something stranger, waiting at the end of the road, where the energy we would need to concentrate does something no one intended. To see it, we have to look at a particle's own built-in fuzziness, a length that belongs to the particle itself. Every particle, it turns out, has a size below which its position simply cannot be pinned, a built-in fuzziness that belongs to the particle itself. This is different from the particle's physical bulk. An electron, as far as we can tell, has no size at all in the usual sense. It behaves like a point, yet there is still a distance associated with it, a scale below which the very idea of locating it precisely breaks down. That scale is called the Compton wavelength, named for the American physicist Arthur Compton. Compton found his name attached to this length through an experiment in the early 1920s. He was studying what happened when X-rays bounced off electrons, and he found that the X-rays came away with a longer wavelength than they went in with, as if they had lost energy in the collision. The only way to explain it was to treat the X-ray as a particle, a photon, colliding with the electron like two balls on a table, one handing energy to the other. It was powerful, direct evidence that light really does come in particle-like packets, and it helped cement the quantum picture. Out of the mathematics came a characteristic length for the electron, its Compton wavelength. Here is what that length means for our purposes. To locate a particle within a distance, you need a probe with a wavelength at least that short, carrying an energy at least that high. The Compton wavelength is the distance at which the probe's energy becomes so large that it equals the energy locked up in the particle's own mass. And when your probing energy reaches the particle's own mass energy, something new can happen. The energy you're pouring in can create a brand new particle, a twin, right there in the collision. This is one of the strangest results of combining quantum mechanics with relativity. Einstein taught that energy and mass are two faces of one thing, that energy can freeze into mass, and mass can melt into energy. So when you try to pin an electron down to within its Compton wavelength, you are hitting it with enough energy to conjure a fresh electron and its antimatter twin out of the collision. You went looking for one electron, and now there are 3 particles in the region. You have not located your electron more precisely. You have muddied the water by making more particles just like it. So the Compton wavelength marks a soft flaw of a kind. Try to probe a particle below that scale, and instead of a sharper picture, you get a swarm of new particles, and the notion of this one particle right here dissolves. It is the point where measurement stops clarifying and starts multiplying. Now notice the crucial feature of this length, the one that matters most for where we are going. The Compton wavelength depends on the particle's mass, and it depends on it in reverse. The heavier the particle, the shorter its Compton wavelength. A light particle, like an electron, has a relatively long Compton wavelength. A heavier particle has a shorter one, meaning you can pin it down more tightly before the trouble starts, and a truly enormous mass would have a fantastically short Compton wavelength. This gives us a lever. If the Compton wavelength shrinks as mass grows, then to probe smaller and smaller distances we want heavier and heavier probes, more and more concentrated energy. Keep increasing the mass, and the Compton wavelength keeps falling, promising access to ever tinier scales. On this logic, there seems to be no flaw at all. Pile on enough mass, and the Compton wavelength drops as far as you like, right down past the Planck length and beyond. Except that a second length is also in play, and it runs the opposite way. As mass grows, this other length does not shrink. It grows. It is the size of the black hole that a given mass would form, and the moment we set these 2 lengths side by side, the flaw we have been chasing finally appears. Take any amount of mass and squeeze it small enough, and it will collapse into a black hole, a region where gravity has grown so strong that nothing, not even light, can escape. Every mass has a critical size for this, a radius to which you would have to compress it for the trap to close. That critical size is called the Schwarzschild radius, and it is the edge of the black hole, the boundary from within which nothing returns. The name comes from Karl Schwarzschild, a German physicist and astronomer, and the circumstances of his discovery are worth remembering. In 1915, Albert Einstein published his general theory of relativity, a new description of gravity as the bending of space and time by mass. The equations were formidable. Within months, Schwarzschild found the first exact solution to them, describing the space around a single round mass. He did this while serving in the German army during the First World War, working out the mathematics between his duties on the Russian front. He sent his solution to Einstein, who presented it on his behalf. Not long after, Schwarzschild fell ill from a disease contracted at the front and died, only in his early 40s. His solution outlived him and carries his name to this day. The Schwarzschild radius has a simple property that we need. It grows with mass. The more mass you have, the larger the black hole it would form, and the relationship is direct. Double the mass, and you double the Schwarzschild radius. A black hole with the mass of the Sun would have a radius of about 3 kilometers. A black hole with the mass of the Earth would be smaller, a radius of about 9 millimeters, the size of a marble, and a tiny mass would have a fantastically tiny Schwarzschild radius, far smaller than any particle. For everyday objects, the Schwarzschild radius is absurdly, harmlessly small. To turn the Earth into a black hole, you would have to crush the entire planet down to the size of that marble, which nothing in nature is doing. To turn yourself into a black hole, you would have to compress your body to a size vastly smaller than a single proton. So in ordinary life, this radius is a mathematical curiosity, a boundary drawn far inside anything real, never actually reached. But hold on to the direction it runs. The Schwarzschild radius grows when mass grows. The more energy and mass you concentrate, the larger the black hole boundary that surrounds it. This is the exact opposite of the Compton wavelength, which shrank as mass grew. One length falls as you pile on mass, the other rises. The two are moving toward each other, and that is the setup for the heart of this whole story. We have found two natural sizes tied to any lump of mass or energy. The Compton wavelength, from the quantum world, which tells you the smallest region within which you can meaningfully locate the mass, and which shrinks as the mass grows. The Schwarzschild radius, from gravity and relativity, which tells you how large a black hole that mass would wear, and which grows as the mass grows. One belongs to the quantum, one belongs to gravity, and they answer to opposite instincts about mass. For a light particle, the quantum length is large, and the gravitational length is vanishingly small, so gravity is no concern at all. As you make the probe heavier, the quantum length shrinks and the gravitational length swells. Somewhere, inevitably, the two must cross. There must be a mass at which the smallest region you can localize the particle into is exactly the same size as the black hole that particle would form. At that crossing, quantum fuzziness and the edge of a black hole become the same distance. That crossing point is the Planck scale, and it is where the answer to our question has been hiding all along. In the next chapter, we watch the two lines meet. Picture two lines drawn on the same page, one falling and one rising. The falling line is the Compton wavelength, the quantum fuzziness of a probe, which shrinks as you make the probe heavier. The rising line is the Schwarzschild radius, the size of the black hole that same probe would form, which grows as you make it heavier. Start on the left with a light probe, an ordinary particle, and the two lines are far apart. The Compton wavelength is high, the Schwarzschild radius is far below it, hugging the bottom of the page. Gravity for such a small mass is utterly beside the point. Now walk to the right, making the probe heavier at every step. The Compton wavelength slides downward, because a heavier probe can be pinned into a smaller region before new particles start appearing. At the same time, the Schwarzschild radius climbs upward, because a heavier probe wears a larger black hole. The two lines lean toward each other, and because one is falling while the other is rising, they must, at some single point, cross. That crossing is not a vague region. It is a definite place, set by the three constants we have been carrying all along: the speed of light, Newton's constant, and Planck's constant. When you write down the Compton wavelength and the Schwarzschild radius, and ask where they become equal, the same combination that built the Planck length falls out of the algebra. The two lines meet at a distance of about 10 to the minus 35 meters, the Planck length itself. They also meet at a particular mass, which we will name in a moment, and at a particular energy. Sit with what this crossing means, because it is the whole answer in miniature. To the left of the crossing, in the ordinary world, the quantum length is the one that matters. When you probe a particle, you worry about its Compton wavelength, about making new particles, about Heisenberg's trade. Gravity is so far below that you never think about it. The Schwarzschild radius sits harmlessly at the bottom of the page, a number so small it plays no part in any experiment. But at the crossing point, gravity climbs all the way up to meet the quantum world. the black hole boundary of your probe becomes exactly as large as the region you were trying to squeeze it into. The two effects you could safely keep in separate rooms are now the same size, standing in the same doorway, and that is precisely the Planck scale. It is the mass, the length, and the energy at which the quantum fuzziness of a thing and the gravitational reach of a thing become one and the same. This is why the Planck length is special and not just small. It is not merely a tiny number that happened to fall out of some constants. It is the exact place where two great effects, which spend all of ordinary physics ignoring each other, are forced to become equal partners. Below the proton, gravity sleeps. At the Planck length, gravity wakes up and stands shoe-to to shoulder with the quantum, and once the two lines have crossed, everything changes character. Keep walking to the right, past the crossing, and now the Schwarzschild radius is the higher line. The black hole boundary is now larger than the quantum region. From here on, adding more energy no longer sharpens your view. It makes the black hole bigger, and it makes the region you can resolve larger, not smaller. The road that always led downward turns around and starts heading back up. That turnaround is the deepest and strangest idea in this whole story, and it deserves to be told slowly on its own. But before we walk into it, we should stop at the crossing point and pick up the mass that lives there. It is called the Planck mass, and unlike everything else in this story, it is not absurdly large or absurdly small. It is a speck you could very nearly see. Everything at the Planck scale is extreme. The Planck length is smaller than anything imaginable, dozens of powers of 10 below a proton. The Planck time, which we will reach shortly, is briefer than any interval physics can name. The Planck energy is larger than any energy a machine has ever produced. Each of these is out at the far edge of the possible, far past the reach of the human world. And then there is the Planck mass, which breaks the pattern completely. The Planck mass is about 22 millionths of a gram. That is it. It is not a colossal number and not a vanishing one. It is roughly the mass of a flea's egg, or a barely visible speck of dust, the kind of mote you might catch in a shaft of afternoon light. You could, in principle, set it on the pan of a good laboratory balance and watch the needle move. Of all the Planck quantities, this is the one you could almost hold. That should feel strange, and it is worth sitting with the strangeness rather than rushing past it. Every other Planck quantity is unreachable by definition, yet the mass that sits at the same crossing point, the mass where quantum fuzziness and the black hole boundary become equal, is an ordinary speck you could lose on your fingertip. How can the doorway to the most extreme physics in the universe be guarded by something as unremarkable as a fleck of dust? The resolution is that mass, energy, and size do not scale together in the way our intuition expects. The Planck mass is a small mass by human standards, but it is an enormous mass for a single particle. Remember that the heaviest particles we know, the ones made in the great colliders, are still fantastically lighter than a speck of dust. The Planck mass is heavier than the heaviest known particle by about 17 powers of 10. So while it is a trifle on a kitchen scale, it is a monster when you try to pack it into one point, into a single quantum probe. And that is the real meaning of the Planck mass. It is the mass a single probe would need to carry for its own gravity to matter as much as its quantum nature. To reach the Planck length by the honest method, hitting a target with a probe, you would have to concentrate the Planck mass, 22 millionths of a gram, into a region smaller than a proton in a single quantum object. A speck of dust is harmless spread across its normal size. Crushed into a point, it becomes the most violent thing in physics. This is why the Planck mass being ordinary is not a comfort but a warning. It tells you that the barrier we're approaching is not about needing some unthinkable amount of stuff. It is about needing an ordinary amount of stuff placed in an impossible way, squeezed into an impossibly small point, at an impossibly high energy. The stuff is nothing. The concentration is everything. The energy that goes with the Planck mass is the Planck energy, and by Einstein's link between mass and energy, that fleck of dust corresponds to a truly staggering amount of energy. comparable, in a single particle collision, to the energy of a car moving at highway speed, all packed into one subatomic point. That is the energy you would have to reach to probe the Planck length, and it is exactly at that energy that the road turns around, and the harder you push, the less you see. That turnaround is the heart of the whole matter, and now we can finally walk into it. Here is the idea the entire climb has been building toward, and it is worth stating as plainly as it can be said. For the whole history of physics, the rule has been simple: to see something smaller, use more energy, shorter wavelength, higher energy, finer detail. This rule carried us from a hair down to an atom, from an atom into the nucleus, from the nucleus down to the quarks inside the proton. Every step deeper cost more energy, and every time we paid, we saw more. The road went one way, and it always worked. At the Planck energy, the road turns around. The reason is the crossing we just watched. Below the Planck energy, adding energy shrinks the region you can resolve, because your probe's quantum wavelength is the limiting length, and that wavelength keeps falling. But once you reach the Planck energy, the black hole boundary of your probe catches up to the quantum wavelength, and from that point on, the black hole boundary is the larger of the two. Push past the Planck energy, and the thing that grows is the Schwarzschild radius. Your probe is now so concentrated that it forms a black hole, and the more energy you add, the bigger that black hole gets. Follow what this does to your measurement. You're trying to look at a smaller and smaller spot. You pour in more energy to sharpen the view, as you always have. But now the energy you're pouring in forms a black hole, and that black hole is larger than the spot you were trying to see. The region you can actually resolve is no longer your probe's tiny wavelength. It is the size of the black hole, and the black hole is growing. You have added energy and made the picture blurrier. You have paid more and seen less. This is the turnaround, and it is unlike anything in ordinary experience. Imagine a camera that took sharper photographs the more you zoomed in, right up to a point, and then, past that point, every further zoom made the image blurrier instead of clearer, and no adjustment could reverse it. The Planck length is that point. It is the sharpest the universe will ever let any photograph be. Approach it from above, from larger distances, and detail improves. Try to push below it, and detail is destroyed, not by any flaw in the camera, but by the energy the camera itself must use. So there is a genuine minimum to the size of the region you can probe, and it is the Planck length. Not because space necessarily comes in tidy pixels of that size, a point we will be careful about later, but because the very act of trying to measure anything smaller defeats itself. The energy required to resolve a sub-Planck distance is enough to form a black hole larger than that distance, which swallows the very detail you were reaching for. The measurement erases its own answer. This is what it means to say the universe forbids measuring below the Planck length. It is not a rule written on a wall that we must obey. It is a trap built into the structure of the world, into the way relativity, quantum mechanics, and gravity fit together. The three constants that seem to be from three unrelated stories were, all along, describing the three walls of a single box, and the Planck length is the floor of that box. To make this fully concrete, we should look closely at exactly what forms when you try, at what happens to the little region of space you are hoping to inspect. What forms is a horizon, and a horizon, by its nature, hides what is behind it. The answer you are reaching for is placed on the far side of a one-way door. Let us do the experiment in imagination carefully and watch it fail in the exact way the physics says it must. You want to measure a distance smaller than the Planck length. You know the rule by now. To resolve a small region, you must deliver energy into it, and the smaller the region, the more energy you must deliver. So you build the ultimate probe and aim it at a spot far smaller than a proton, far smaller even than the reach of the Large Hadron Collider, down toward the Planck scale, and you pour in the enormous energy that such fine resolution demands. As that energy concentrates into the tiny region, gravity finally has its say. Energy, by Einstein's relativity, gravitates just as mass does. Concentrate enough of it in a small enough space, and the space responds the way it responds to any dense lump of mass. It curves sharply and closes over. A horizon forms, the boundary of a black hole, sealing off the region you are trying to inspect. And here is the cruel precision of it. The horizon that forms is about the size of the Planck length, or larger, and it grows if you add still more energy. So at the very moment you deliver enough energy to resolve a sub-Planck distance, that energy wraps the region in a horizon at least a Planck length across. Whatever detail was inside is now behind the horizon, and a horizon is the one barrier in physics that truly cannot be seen past. No light, no signal, no information escapes from within it. You have not measured the tiny region. You have hidden it, permanently, behind a one-way door of your own making. This is why the limit is absolute rather than merely difficult. With most barriers in science, you can imagine a cleverer instrument slipping past. Here, cleverness makes it worse. Any conceivable method of resolving a sub-Planck distance comes down to concentrating energy there, because that is what resolution is, and concentrating that much energy there always forms a horizon that swallows the answer. There is no probe subtle enough to avoid it, because the problem is not the subtlety of the probe, but the energy any probe must carry. The finer you aim, the more surely you seal the region away. Notice how neatly this closes the circle we opened at the very start with your hand halving a distance again and again. In pure geometry, on the page, nothing stops the halving. But in the real universe, the act of checking a halved distance requires a measurement, and the measurement requires energy, and below the Planck length that energy builds a wall around the very thing you wanted to see. The words shorter and longer keep their meaning on paper down to any size you like. In the world, they lose their footing at the Planck length, because no possible act of measurement can distinguish 2 points closer together than that. So the Planck length is not the size of some smallest brick, at least not necessarily. It is the smallest distance that measurement can ever resolve before measurement destroys itself. It is an operational flaw, a limit on what can be known, drawn by the same hand that set the speed of light and the strength of gravity. Below it, the universe does not necessarily stop, it simply stops answering. And the same reasoning that gives a smallest measurable length gives a shortest meaningful time, because in relativity space and time are bound together, two aspects of one fabric. If there is a flaw to distance, there is a flaw to duration, the briefest instant physics can honestly speak of. That instant has a name and a place in the very first moment of the universe. The speed of light does more than cap how fast things move. It ties distance and time together so tightly that you cannot have one without the other. Light crosses a certain distance in a certain time, always at the same rate, so any length can be read as a duration, and any duration as a length. This is why, once we have a smallest meaningful length, a smallest meaningful time follows almost automatically. Ask how long light takes to cross a single Planck length, and you have defined the Planck time. The Planck time is about 10 to the minus 44 seconds. Written out, that is a decimal point followed by 43 zeros before the digits begin, in seconds. It is as far below 1 second as the Planck length is below the everyday world. If you tried to count off Planck times the way a clock counts seconds, you would never finish, not in the entire age of the universe. There have been fewer seconds since the beginning of time than there are Planck times in a single blink, and the comparison does not even come close. The Planck time is the shortest interval that our physics can describe honestly. Below it, the same trouble that afflicts the Planck length afflicts duration. To mark off a time shorter than the Planck time, you would need to measure a change over a distance shorter than the Planck length, and that, we have seen, cannot be done without sealing the region behind a horizon. So the Planck time is a flaw on the meaningful measurement of time, just as the Planck length is a flaw on the meaningful measurement of distance. Ask what happened in an interval shorter than the Planck time, and our theories give no honest answer. This flaw has a remarkable place in the story of the universe itself. Run the history of the cosmos backward, from now toward the beginning, and everything grows hotter and denser as it shrinks toward the initial moment. Our physics can follow this backward run a very long way, past the formation of atoms, past the forging of the first nuclei, back to the smallest fraction of a second after the beginning. But there is a wall, and the wall is the Planck time. The earliest moment our theories can describe is 1 Planck time after the beginning, and no closer. That first interval, from the beginning to 1 Planck time, is called the Planck epoch. During it, the entire observable universe was squeezed into a region so small and so dense that the whole cosmos was, in effect, at the Planck scale everywhere at once. Quantum fuzziness and gravity were equally strong across all of it. And because we have no theory that handles both at once, we simply cannot say what happened in that first sliver of time. It is not that the details are hard to work out, it is that the equations we trust break down and give nonsense when pushed into the Planck epoch. So the Planck time marks the edge of the describable past. Physicists speak confidently about the universe from 1 Planck time onward, through its expansion and cooling, the whole grand history. Before that, in the first 10 to the minus 44 seconds, there is a curtain we cannot yet see behind. The Planck scale draws the curtain, in time as well as in space. The beginning of the universe hides behind the same wall that hides the smallest distance, and for the same reason. What lies behind that curtain, at the Planck scale, is something no one has ever observed, and can only be imagined through the mathematics. But one physicist gave us a vivid picture of it, a way to imagine what space and time might be doing down at the smallest scale, where the smooth fabric of the everyday world may dissolve into something restless and churning. His name was John Wheeler, and he called it quantum foam. John Archibald Wheeler was an American physicist with a rare gift for naming things. He gave us the term black hole, which before him had no snappy name at all. He popularized the word wormhole for a tunnel through space-time, and he coined a phrase for what he imagined space itself becomes at the very smallest scale. He called it quantum foam. Wheeler worked at the deep end of physics for decades, taught many of the field's great figures, and had a habit of turning difficult ideas into images you could almost see. Quantum foam is his image for the Planck scale. Here is the picture he was reaching for. On the scale of everyday life, and even on the scale of atoms, space looks perfectly smooth. It is the calm, featureless stage on which everything happens, flat and quiet and continuous. A ball rolls across it without a bump. Light travels through it in a straight, untroubled line. Nothing about ordinary space suggests any texture at all. It is the very picture of smoothness, the smooth page we imagined halving at the start. But zoom in, Wheeler said, all the way down toward the Planck length, and that smoothness may be an illusion of distance, the way a calm sea looks like glass from an airplane and like a chaos of waves from a rowboat. At the Planck scale, the same quantum uncertainty that jitters particles should jitter, space and time themselves. Recall that the uncertainty principle forbids perfect stillness. A quantum thing can never sit exactly at rest with exactly zero energy, because that would pin down too much at once. So even empty space, at the smallest scale, cannot be perfectly still and flat. Instead, according to this picture, space at the Planck scale seethes. Tiny regions curve and flicker. The energy in empty space fluctuates from moment to moment, and because energy curves space, those fluctuations bend the geometry this way and that, faster than any clock could follow. There may be tiny black holes forming and vanishing, tiny bridges and tunnels opening and closing, the whole structure churning and frothing like the surface of boiling water or like the foam on a breaking wave, hence the name. The smooth stage, seen closely enough, may be no stage at all but a restless froth. It is important to be honest about the standing of this picture. Quantum foam is not an established fact. No one has seen it, and, as this whole story argues, no one may ever be able to. It is a physicist's informed imagining of what should happen when quantum uncertainty is applied to space and time at the Planck scale, using the pieces of theory we have. Different approaches to the deep physics disagree about the details, and some question the picture entirely. Wheeler offered it as a way to think, a vivid guess at the character of the Planck world, not as a measured result. Still, the picture captures something real about why the Planck length matters. It marks the scale where the comfortable idea of smooth, passive space is expected to fail. Above it, space is the quiet backdrop of all our physics. At it, space may become an actor, violent and uncertain, as much subject to quantum rules as any particle. If that is right, then asking for a distance smaller than the Planck length is like asking for a smooth measurement across the surface of boiling water. The ruler itself would be tossed by the froth. Whether or not the foam is exactly Wheeler's froth, the underlying reason for the Planck scale's strangeness is firm. It is the one place where our two greatest theories, the quantum theory of the small and the relativity of gravity, are both loud at once, and where neither can be silenced. That collision is the true heart of the matter, and it is time to look straight at it. Modern physics rests on two great theories, and they are each, on their own, astonishingly successful. The first is quantum mechanics, the physics of the very small, which describes particles, atoms, light, and the forces that bind them. It has been tested to extraordinary precision, and it has never failed a test. The second is general relativity, Einstein's theory of gravity, which describes space, time, and the motion of planets, stars and galaxies as the bending of a smooth space-time fabric by mass and energy. It too has passed every test, from the bending of starlight to the ripples we now catch from colliding black holes. The trouble is that these two triumphs do not get along. They are built on different foundations and speak different languages. Quantum mechanics treats space and time as a fixed, smooth background against which quantum things jitter and play. General relativity makes space and time themselves the dynamic thing, bending and stretching, with no fixed background at all. One theory needs a firm stage, the other says the stage is part of the show. For most of physics, this clash never surfaces because the two theories rule different kingdoms. They stay apart through a simple division of labour. Quantum mechanics matters where things are very small, like atoms, where gravity between the tiny masses is so absurdly weak it can be ignored completely. General relativity matters where things are very massive, like stars and galaxies, where quantum effects wash out and the smooth picture holds. Small and light, use the quantum. Large and heavy, use relativity. In almost every situation in the universe, one theory is loud, and the other is so quiet you never hear it. So you use the loud one and get the right answer, but the Planck scale is the one place where both are loud at once. It is, by its very definition, the scale where a thing is small enough for quantum mechanics to shout and, at the same time, dense enough in energy for gravity to shout just as loudly. That is what the crossing of the two lines meant. At the Planck length, the quantum fuzziness of a thing and the gravitational curvature of a thing become equal. You can no longer keep one theory loud and the other quiet. Both demand a say, and both must be used together. And when you try to use them together, they give nonsense. Take the equations of general relativity and try to apply quantum rules to space-time itself, the way you would to any other field, and the calculations spit out infinities, answers of endless size that mean the method has failed. The two theories, forced into the same room, contradict each other. This is not a small technical snag. It is the deepest unsolved problem in fundamental physics, the reason there is no accepted theory of what happens at the Planck scale. We call the missing theory quantum gravity, and finding it is the great unfinished task. So the Planck length is not just the smallest measurable distance, it is the address of physics' greatest open question. It is where our two masterpieces meet and fail, where the smooth space-time of Einstein and the jittering quantum of the atom cannot both be right in their present forms, and where some deeper theory, not yet found, must take over. The floor beneath measurement is also the frontier of understanding, We cannot measure below it, and we cannot yet calculate below it either. That has not stopped physicists from trying to build the missing theory. Several bold attempts exist, each a different guess at what space-time becomes at the Planck scale, and each, remarkably, seems to carry a smallest length inside it in its own way. The most famous of these attempts replaces the point-like particle with a tiny vibrating string, and it is worth seeing how a string of all things builds in a shortest distance. For most of the 20th century, physics pictured the basic bits of matter as points, particles with no size at all, sitting at single locations in space. String theory begins by changing that one picture. It proposes that the most basic things are not points, but tiny vibrating strings, unimaginably small loops and threads of energy, and that every particle we know is one of these strings vibrating in a particular way. An electron is a string humming one note. A quark is a string humming another. Matter, in this view, is music, and the particles are the notes. The strings are about the size of the Planck length. That is already telling. String theory did not set out to install a minimum length by hand. It arose from other motivations, chiefly the hope of uniting all the forces, including gravity, in a single quantum framework. But once you replace points with strings of roughly Planck size, a shortest meaningful distance comes along almost as a bonus. You cannot probe much below the size of the string itself, because there is nothing smaller than the string to do the probing. The point-like tools are gone. There is a deeper and stranger reason string theory resists sub-Planck distances, and it goes by the name of duality. In the mathematics of string theory, a curious symmetry appears. If you try to squeeze a dimension of space down smaller and smaller, below the Planck length, the equations describing that tiny world turn out to be exactly the same as the equations describing a large world, above the Planck length. Small and large fold into each other. A distance far below the Planck length is not a new, smaller realm at all. It is a mathematical mirror image of a large one, describing the same physics in different words. Sit with how odd that is. In ordinary thinking, smaller is always a fresh direction. You can keep going down, and each level is new. String theory's duality says that once you cross below the Planck length, down stops being a new direction. You come out the other side, back into a large world you have already described. It is as if the number line, past a certain point, wrapped around and rejoined itself. There is no true below the Planck length to reach, because trying to reach it just brings you back to somewhere above it. The shortest distance is not a wall you hit, but a fold you slide along. This gives the Planck length a different flavour in string theory than in the black hole argument we built earlier. In the black hole picture, the barrier is that measurement destroys itself, sealing sub-Planck regions behind horizons. In string theory, the barrier is that sub-Planck regions are not even separate places. The two pictures come at the floor from different directions, and both arrive at the same rough length. The Planck length as the shortest distance that means anything. That agreement, from very different starting points, is part of why physicists take the length seriously. It should be said plainly that string theory is not confirmed. It is a vast, mathematically rich framework, admired for its elegance and its natural inclusion of gravity. But it has not been tested by experiment, and it may not be the correct description of nature. Its strings are so small that seeing one directly would require exactly the Planck scale energies we cannot reach. So its minimum length is a feature of the theory's mathematics, not yet a measured fact about the world. But string theory is not the only serious attempt at quantum gravity, and it is not the only one that finds a smaller scale. A very different approach starts not from strings, but from space itself, and asks whether space, like matter, might come in indivisible grains. That approach is called loop quantum gravity, and its answer is as concrete as a floor made of tiles. String theory keeps space smooth and fills it with tiny strings. Loop quantum gravity takes the opposite tack. It leaves the particles more or less alone, and asks a bolder question about space itself. What if space is not smooth at all? What if space, like matter, comes in smallest pieces, indivisible grains that cannot be cut in half? In this picture, the smooth space of our experience is an illusion of scale, the way a fabric looks continuous until you see the individual threads. The idea grows out of taking Einstein's general relativity and applying quantum rules directly to it, treating the geometry of space as the thing to be quantized. When physicists carry this through, something striking emerges from the mathematics. Area and volume come out grainy. Just as energy comes in the smaller step set by Planck's constant, area comes in smaller steps, and there is a smallest possible patch of area, close to the Planck length squared, below which no smaller area exists. You cannot have half of that smallest patch any more than you can have half of the smallest step of energy. So in loop quantum gravity, if you could look closely enough at a region of space, you would find it built from tiny chunks of volume, joined along tiny patches of area, all of them near the Planck scale. Space would be less like a smooth sheet, and more like fine chainmail, countless smallest links woven together, appearing seamless only because the links are so unthinkably small. The theory describes these links with a structure called a spin network, a web of connections that, viewed from far away, weaves itself into the smooth space-time of ordinary experience. This gives the clearest possible meaning to a smallest length. In this picture, the Planck length is not only the smallest distance you can measure, it is the smallest distance there is. Space does not extend below it, because space is made of pieces that size, and there is simply nothing underneath. Asking for a distance shorter than the Planck length would be like asking for a fraction of a single atom of space. The question would have no referent because the grain is the smallest thing, and it does not divide. Loop quantum gravity and string theory disagree deeply about almost everything. One makes space smooth and adds strings. The other makes space itself grainy. They start from different mathematics and paint different portraits of the deep world, and yet they agree on the headline. Both find that the Planck length is a flaw, a shortest meaningful distance, below which the ordinary idea of length gives out. Two rival theories, born of different instincts, point to the same scale as the edge of space. When rivals agree on a conclusion while disagreeing on everything else, the conclusion earns extra weight. Loop quantum gravity, like string theory, remains unconfirmed. It is a serious, developed framework, worked on by many capable physicists, but it has not been tested against experiment at the scale where it makes its boldest claims, and it faces hard, unsolved problems of its own. Whether space is truly grainy is not known. What we can say is that a leading attempt to unite quantum mechanics and gravity finds graininess natural, and finds the grain sitting right at the Planck length. Both of these theories change the deep picture of space, but there is a simpler, more direct way that a smallest length can enter physics without committing to strings or grains at all. It works by adjusting the uncertainty principle itself, adding a new term that plants a flaw beneath position. That adjustment is called the generalized uncertainty principle. Recall Heisenberg's uncertainty principle, the ironclad trade between position and momentum. The more tightly you fix where a particle is, the more wildly uncertain its momentum becomes, with Planck's constant setting the terms. In its usual form, that principle places no floor on position. It says you can pin a particle's location as tightly as you like, down to any distance at all, as long as you accept an ever larger uncertainty in its momentum in return. Position, in ordinary quantum mechanics, can in principle be made perfectly sharp. But the black hole argument we built earlier suggests that cannot really be true. We saw that pinning a particle into an extremely small region requires an extremely large energy, and that beyond the Planck scale, that energy forms a black hole whose horizon grows as you add more. So squeezing position too tightly should, past a point, start increasing your uncertainty rather than decreasing it, because the horizon widens. Ordinary uncertainty leaves this out. It knows about the quantum but not about gravity. The generalized uncertainty principle is the repair. It takes Heisenberg's trade and adds a second term, a gravitational term, that grows with the energy of the probe. At low energies, this new term is tiny and changes nothing, so ordinary quantum mechanics is recovered exactly as it must be. But at high energies, near the Planck scale, the new term takes over, and it works in the opposite direction from the usual one. The usual term says more energy sharpens position. The new term says more energy, past the Planck scale, blurs it again, because the growing black hole horizon smears the location out. Put the two terms together, and the uncertainty in position no longer falls forever as you push harder. It falls, reaches a minimum, and then rises. There is a smallest value it can take, a best possible sharpness, and that smallest value is about the Planck length. No matter how you arrange your probe, no matter how much energy you pour in, you cannot fix a particle's position more tightly than the Planck length, because past that point, the gravitational term wins and the fuzziness grows again. The flaw appears directly in the equation for uncertainty. This is a satisfying way to see the limit, because it needs no elaborate machinery, no strings, no grains of space. It simply takes the uncertainty principle everyone already trusts and adds the one ingredient it was missing, the gravity of the probe itself. Do that, and a minimum length falls out sitting at the Planck scale, in agreement with everything else we have found. The same flaw that emerged from black holes, from string theory, and from loop quantum gravity emerges again here, from a small honest correction to Heisenberg. Once again, the caution applies. The generalized uncertainty principle is a well-motivated modification, and it captures the black hole argument in compact form, but its exact shape is not settled, and it is not confirmed by experiment. Different approaches to quantum gravity suggest slightly different versions of the extra term. What they share is the conclusion, the same conclusion this whole story keeps circling. There is a shortest meaningful length near the Planck length, and it comes from gravity setting a flaw beneath the quantum trade. All of these ideas concern how small you can measure or how small space can be. But the Planck length shows up in another, even stranger place, one that changes how we count what a region of space can hold. It appears when we ask how much information can fit inside a volume, and the answer, astonishingly, is written on the surface. Ask how much information you can pack into a region of space, and common sense gives a confident answer. Information takes room, so a bigger volume should hold proportionally more, and doubling the volume should double the capacity. A larger box holds more than a smaller box. This is how we think about hard drives, libraries, and warehouses. Capacity grows with volume, with the amount of inside. It is one of the most natural assumptions we make about space. Physics says that assumption is wrong at the deepest level, and the correction involves the Planck length in a way no one expected. The maximum information a region can hold is set not by its volume, but by its surface area, by the size of the boundary that wraps around it, and that area is measured in Planck-sized patches. Divide the boundary of a region into little squares, each one Planck length on a side, count how many squares it takes to cover the surface, and that count sets the maximum information the entire volume inside can contain. The capacity lives on the surface, tiled in Planck areas. This is called the holographic principle, and the name is chosen with care. An ordinary hologram is a flat piece of film that stores a full three-dimensional image so that a two-dimensional surface encodes a three-dimensional scene. The holographic principle says the universe may work the same way. The full contents of a three-dimensional region can be captured completely by information written on its two-dimensional boundary, with each Planck-sized patch of that boundary holding a single smallest unit of information. The inside is, in a sense, a projection of what is written on the edge. The idea sounds outlandish, and it did not come from idle speculation. It came from thinking hard about black holes, and about the strange fact that a black hole's capacity for information turns out to depend on the area of its horizon, rather than the volume it encloses. Physicists including Gerard 't Hooft and Leonard Susskind took that black hole result and proposed it as a general truth about all regions of space, not just black holes. Wherever you draw a boundary, the most it can enclose is fixed by the boundary's area in Planck units. The three-dimensional world may be at bottom, a story written in 2 dimensions. Notice the role the Planck length plays here. It is the size of the smallest patch of surface that can hold 1 unit of information, the pixel of the cosmic hologram. If the Planck length were different, the capacity of every region would be different. The floor of measurable distance is also, in this picture, the size of the fundamental cell of information, the smallest tile in the surface on which reality is written. The same tiny length that limits what we can measure sets the resolution of the universe's storage. This deepens what the Planck length means. It began, in this story, as the smallest distance we could measure, an operational flaw drawn by black holes. It grew into the smallest distance that might exist, a structural flaw in space itself. Now it becomes something more, the size of the basic unit in which the universe accounts for its own contents. 3 faces of 1 length, all pointing at the same scale, arrived at from measurement, from geometry, and from information. The holographic principle rests on a specific, hard result about black holes, one of the most celebrated results in modern physics, in which a black hole's hidden information is counted in Planck-sized patches of its horizon. That result is worth meeting directly, because it is the firmest place where the Planck area enters real, respected physics, and it was found by 2 people thinking carefully about what a black hole truly is. A black hole seems, at first, like the simplest object imaginable. Whatever falls in is hidden forever behind the horizon, and from outside a black hole appears to be described by just a few numbers, its mass, its spin, and its charge. 2 black holes with the same mass, spin, and charge look identical, no matter what fell in to make them, whether stars or planets or encyclopedias. This apparent simplicity troubled physicists deeply, because it seemed to clash with a bedrock law, the law that information is never truly lost, and that disorder, called entropy, always tends to grow. The worry was sharp. If you drop a hot, disordered object into a black hole, its entropy seems to vanish from the universe, hidden behind the horizon, and the total disorder outside goes down, which the law forbids. In the early 1970s, a graduate student named Jacob Bekenstein made a bold proposal to save the law. A black hole, he argued, must itself carry entropy, a measure of hidden disorder, so that when something falls in, the black hole's own entropy grows to make up for what was lost, and he proposed that this entropy is proportional to the area of the horizon. Stephen Hawking at first doubted the idea, then, working through the quantum behavior of fields near a horizon, found something that turned doubt into confirmation and went further still. Black holes, Hawking showed, are not perfectly black. They glow ever so faintly, giving off a slow trickle of radiation, now called Hawking radiation, and so they have a temperature, and anything with a temperature has entropy. When Hawking worked out the exact amount, he found Bekenstein had been right in form, and he fixed the precise value. The entropy of a black hole is its horizon area divided by 4 Planck areas. Sit with that formula, because it is remarkable. A Planck area is the Planck length multiplied by itself, a tiny square about 10 to the minus 70 meters squared. To find the entropy of a black hole, its hidden information content, you take the area of its horizon and count how many Planck-sized squares would tile it, then divide by 4. The information capacity of a black hole is literally its surface measured in Planck patches. The Planck length, squared, is the unit in which a black hole keeps its books. This is the firm ground beneath the holographic principle, and it is the place where the Planck area appears not as speculation, but as part of a widely accepted result. The Bekenstein-Hawking entropy is one of the deepest formulas in physics, tying together gravity through the horizon, quantum mechanics through the temperature, thermodynamics through the entropy, and the Planck scale through the unit of area. All the great themes meet in a single short equation, and the Planck length sits at its heart, defining the size of the tile. It also sharpened the greatest puzzle about black holes, the question of what happens to the information that falls in. If a black hole slowly radiates away and disappears, as Hawking's work suggests, then what becomes of everything that fell in? Is the information truly lost, breaking the deep law, or is it somehow carried out in the faint radiation? This is the black hole information paradox, and it has occupied the finest minds in physics for decades. It remains not fully resolved, and its resolution is expected to teach us something profound about how space, information, and the Planck scale fit together. So the Planck length is woven into the most respected mathematics we have about black holes. Yet we should now step back and ask the honest, sobering question that a careful listener has surely been holding. Is the Planck length truly a flaw of nature, a real smallest thing? Or is it only the place where our current theories throw up their hands? The difference matters, and honesty requires facing it. We have spent many chapters building the case that the Planck length is a flaw, and the case is strong, but honesty requires drawing a careful line between two very different claims. The first claim is modest and well-founded. At the Planck length, our current theories break down. Quantum mechanics and general relativity, forced together, give infinities and nonsense, and no measurement we can devise can reach below this scale without destroying its own answer. That much follows from physics we trust, and it is not seriously doubted. The second claim is bolder, and it is not proven. It says the Planck length is a real physical smallest distance, an actual pixel of space, below which nothing exists, the way loop quantum gravity's grains would make it. This is a hypothesis, an attractive and much discussed one, but it has not been established. It could be that space really is grainy at the Planck scale. It could also be that space stays smooth far below the Planck length, and that the Planck length marks only the limit of our knowledge, not a limit of nature. These are different statements, and the evidence we have supports the first far more firmly than the second. The distinction can be put simply. The Planck length is certainly a flaw on measurement, a limit on what can be known. Whether it is also a flaw on existence, a limit on what can be, is an open question. The universe may forbid us from measuring below the Planck length while still, in some sense we cannot check, having structure there. A limit on knowing is not automatically a limit on being, and careful physicists keep the two apart. There is a genuine tension that makes the strong version harder to accept, and it comes from relativity, from the very speed of light we leaned on so heavily. Einstein's relativity says that lengths are not absolute. A ruler in motion is measured as shorter than the same ruler at rest, and different observers, moving differently, disagree about lengths. But if the Planck length were a fixed, absolute smallest distance, the same for everyone, how could it also shrink for a moving observer, as relativity insists all lengths do? A truly universal minimum length seems to sit uneasily with the relativity that helped define it. Physicists take this tension seriously, and there are proposed ways around it. Some suggest that the rules of relativity are gently modified near the Planck scale, so that the minimum length can be the same for all observers after all, an idea explored under names like doubly special relativity. Others suggest the minimum length is not a sharp distance but a fuzziness, a smallest resolvable area or a statistical flaw which sidesteps the problem of a moving ruler. These are active areas of research, unsettled, and it is right to say so plainly rather than paper over the difficulty. So the calm, honest summary is this. The Planck length marks, with confidence, the scale where our best theories fail and where measurement defeats itself. It marks, with much less confidence, a possible smallest distance built into the fabric of reality. The first is a statement about the edge of our understanding. The second is a guess, well motivated but unconfirmed, about the nature of space. The wonder of the Planck length does not require the bolder claim. It is astonishing enough that the three deepest constants agree on a scale where knowledge itself gives out. And because these are physical claims, not just philosophy, physicists have looked for ways to test them. If space really is grainy at the Planck scale, that graininess might leave a faint fingerprint on the world one patient experiments could hope to catch. Several such searches are underway, reaching for the Planck scale not by brute energy, but by cleverness. If the Planck scale is forever beyond the reach of any collider, as we'll see it likely is, then testing it seems hopeless. But physicists have found sideways paths, clever ways to look for tiny effects of Planck scale structure without ever reaching Planck energies directly. The trick is to let small effects add up over enormous distances or long times, so that a fingerprint far too faint to see up close becomes just barely visible after a very long journey. Several such searches are running now, and their results are already telling us something. The first path watches light from the far reaches of the universe. If space is grainy at the Planck scale, some theories predict that light of different colours would travel at very slightly different speeds through that graininess, the higher energy light lagging or leading by a hair. Over a few meters the difference would be nothing, but over billions of light years it might build into a measurable gap in arrival times. So physicists watch gamma-ray bursts, tremendous explosions in distant galaxies that flash out light across the spectrum at once. If the graininess were there, the different colours from a single burst should arrive at slightly different moments after their long trip across the cosmos. The space telescopes that watch these bursts, including the Fermi Gamma-ray Space Telescope, have caught bursts from billions of light years away and compared the arrival times of high energy and low energy light. And within the precision they can reach, the light of different energies arrives together, with no gap. This does not prove space is perfectly smooth, but it does rule out the simplest versions of Planck scale graininess, the ones that would have smeared the arrival times. Space, as far as these bursts can tell us, is smoothed down past where those simple models predicted texture. The simplest guesses have already failed the test. The second path is stranger and closer to home. A physicist named Craig Hogan reasoned that if the universe is holographic, if its information is written in Planck-sized patches on distant boundaries, then the position of things might carry a tiny, irreducible jitter, a faint blur inherited from the finite resolution of that cosmic hologram. To hunt for it, he helped build an instrument called the Holometer at Fermilab in Illinois, a pair of exquisitely sensitive laser devices designed to detect a holographic jitter far smaller than a proton in the positions of its mirrors. The holometer ran and looked for that jitter, the faint tremor a holographic universe might impose on space itself. It did not find it. Within its sensitivity, space held still, with none of the particular holographic noise Hogan's model predicted. Like the gamma-ray bursts, this is a real result, and it is a negative one. It does not close the book on the holographic principle, which comes in many forms, but it rules out the specific version the holometer was built to catch. The experiment did its honest work and returned a clear answer: no. These searches share a shape worth admiring. They cannot reach the Planck scale by force, so they reach it by patience and cleverness, letting the cosmos itself amplify the tiniest effects. And so far, they have found smoothness where the simplest grainy models expected texture. That is real knowledge, hard won. It tells us that whatever happens at the Planck scale, the easy pictures of it are probably too crude, and the truth is subtler than a simple grid of Planck-sized pixels. But these clever, indirect searches are the only kind we have any hope of doing, and it is worth understanding why. The direct approach, building a machine to reach the Planck energy, runs into a wall so absurd it is almost funny, a gap so vast that no imaginable engineering could close it. Let us finally put real numbers to the energy gap, because it is the plainest way to feel why the Planck scale sits beyond us. Energy at the particle scale is measured in units called electron volts, and their larger cousins. The Large Hadron Collider, our mightiest machine, accelerates protons to an energy of about 14 trillion electron volts when two of them meet head-on. That is a staggering energy to concentrate on a single particle, the product of a 27-kilometer ring and decades of engineering. It is the current summit of human reach. The Planck energy, the energy needed to probe the Planck length, is about 10,000 trillion electron volts. Set the two side by side, the collider reaches around 10 to the 13th electron volts. The Planck energy sits at around 10 to the 28th electron volts. The gap between them is about 15 powers of 10, a factor of 1,000 trillion. Our greatest machine falls short of the Planck energy by that colossal ratio, and closing it is not a matter of a bigger budget or a longer tunnel. Try to picture what a collider that reached the Planck energy would look like. The energy a circular collider can reach grows very roughly with its size. To gain 15 powers of 10 in energy over the Large Hadron Collider, you would need a ring larger than the collider by something like that same enormous factor. The Large Hadron Collider is 27 kilometers around. A Planck collider, scaled up this way, would need to be larger than the Earth, larger than the Sun's whole planetary system, on the order of the distance across an entire galaxy. You would have to build a ring of magnets light years around and power it for the age of a civilization. No conceivable engineering closes a gap like that. It is not that the machine would be expensive or difficult. It is that the machine would be the size of the Milky Way. There is no path from where we stand to a device that reaches the Planck energy by accelerating particles, not with any technology we can imagine, not for any society we can imagine. The direct road to the Planck length, higher energy for smaller distance, works flawlessly for 15 more powers of 10, and then asks for a machine the size of the stars. This is a different kind of impossibility from the black hole barrier we built earlier, and it is worth keeping the two straight. The black hole barrier is a limit of principle. Even if you had the energy, the measurement would seal itself behind a horizon and fail. The energy gap is a limit of practice. Even setting the horizon aside, you could never build a machine large enough to deliver the energy in the first place. The Planck scale is thus doubly protected, walled off both by what the universe forbids and by what engineering can never supply. Together, these two walls explain why the Planck length is likely to remain, forever, a place we understand only through theory and only glimpse through the cleverest indirect searches. We will not photograph it. We will not build the collider that reaches it. We will not measure a distance below it, because the attempt destroys its own answer. What we can do is reason our way to its edge, as we have, and test the fringes of our reasoning with patient experiments that let the cosmos do the amplifying. And so we arrive back where we began, at your hand splitting a distance in half, feeling as though it could go on forever. We have followed that feeling all the way down to the floor. It remains to say, in the simplest words, what we found there and what it means for us, standing as we do so many powers of 10 above the smallest scale in the world. Return to the beginning, to your hand halving a distance, then halving it again, feeling as though nothing could ever stop you. Now you know what stops you. Not your hand and not your tools, but the universe itself, through the way three deep facts about nature fit together. The speed of light, which binds space to time, Planck's constant, which makes energy grainy, and Newton's constant, which lets gravity respond to concentrated energy. Press them together and they name a length, about 10 to the minus 35 meters, below which measurement cannot go. Here is the answer to our question, in the plainest words. You cannot measure anything smaller than the Planck length, because measuring means concentrating energy in a small place, and to resolve a distance that small, you must concentrate so much energy there that gravity closes the region into a black hole, hiding the very thing you were trying to see. Look harder, and you seal the answer away more surely. The floor is not made of any material. It is made of the rules themselves, the same rules that run the whole rest of physics. We found that this floor shows its face again and again, from different directions. It is where the quantum fuzziness of a particle and the black hole it would form become the same size. It is where our two great theories, quantum mechanics and general relativity, both grow loud and then fall into contradiction. It is the size of string theory's strings, and the grain of loop quantum gravity's space, and the floor beneath Heisenberg's trade, and the tile in which black holes and perhaps the whole universe keep their information. So many roads, arriving at the same small number. And we were honest about the edges. The Planck length is certainly the floor of measurement, the place our knowledge gives out. Whether it is also the floor of existence, a true smallest piece of space, we do not yet know, and the searches so far have found smoothness where the simplest grainy pictures expected texture. The wonder does not depend on settling that. It is enough that the deepest constants agree on a scale, and that the scale marks the frontier of everything we understand. Now widen out, and see where this leaves you. You live at a comfortable middle of the universe's scales, unimaginably larger than the Planck length, and unimaginably smaller than the reach of the cosmos. Below you, dozens of powers of 10 down, lies a floor you can reason about but never touch, where space and time may dissolve into something we have no words for. Above you, dozens of powers of 10 up, lies a universe so vast that light needs billions of years to cross it. You stand between two horizons of understanding, one impossibly small, one impossibly large, and the same three numbers govern both ends. The speed of light that caps the Planck scale is the speed of light that carries starlight across the cosmos. The gravity that seals the smallest region is the gravity that shapes galaxies. The quantum grain that jitters a particle is the quantum grain that in the universe's first moment may have seeded everything we see. The very small and the very large are written in one hand, and you, in the middle, are made of the same rules that draw the floor beneath the floor, so the next time you imagine halving a length and halving it again, feeling that easy sense that it could go on forever, hold both truths at once. On paper, it can. In the world, it cannot. And the place where that feeling meets its limit is not a defeat, but one of the most remarkable things we have ever learned about the universe we live in, and about how far down its order reaches before it hides its face.